Hello, my name is Martin Martinez Ruiz. I'm going to present my work named Synthesis and Characterization of Mechanically Alloyed Nanostructure Cubic Molybdenum Tungsten Carbide. In this work, the synthesis and characterization of nanostructure molybdenum tungsten carbide were carried out by mechanical alloying with a mixture of elemental powders at different grinding times. The formation of a solid solution was observed at 150 hours of milling. The first step was the preparation of a mixture made of pure elemental powders of graphite, tungsten, and molybdenum, with the nominal composition of on a weight percent basis of 15, 60, and 25% respectively. A stainless steel container held this mixture under an inner atmosphere, at a ratio in weight of 10 to 1 volts powder. The processing of the mixture was through mechanically alloying for times of 25, 50, 75, 125, and 150 hours in two energy processes, low energy and high energy ball mills at 500 and 1500 revolutions per minute respectively. The phases and morphology at every stage of milling were studied by X-ray diffraction, scanning electron microscopy, high-resolution transmission electron microscopy, and Vickers hardness. Figure 1 shows the X-ray diffraction of the powder particles by a high-energy ball mill at 125 and 150 hours. The intensity of the peak corresponding to the graphite 002 showed a drastic decrease from 125 to 150 hours of milling, which correspond to a 99.74% reduction. This behavior was attributed to the incorporation of graphite into the molybdenum tungsten matrix, occupying the interstitial sites, thus producing the molybdenum tungsten bimetallic carbide of the interstitial solid solution due to the increasing of 110 plane. To determine the distribution of the elements in the powder particles, Figure 2 shows the scanning electron micrographs and corresponding X-ray elemental maps of the sample milled at 150 hours. Figure clearly shows that the sample is composed of tungsten, molybdenum, and graphite, which led to the assumption of the presence of the molybdenum tungsten carbide phase. One of the main characteristics of metallic carbides is hardness. Table 2 summarizes the average values of Vickers hardness obtained for each sample. Hardness increased when the grinding time was increased. 150 hours of milling hardness was higher than that one of the individual carbides, which showed that a new type of carbide in a solid solution was obtained. In conclusions, nanostructure tungsten molybdenum and tungsten molybdenum carbide phases were successfully synthesized by mechanical alloying. Tungsten molybdenum carbide was a BCC crystalline structure with a lattice parameter of 0.3148 nanometers. At the first stage of milling, the tungsten atom substituted the molybdenum atoms, producing the molybdenum tungsten alloys with a BCC crystalline structure. The graphite atoms were introduced to the interstitial position of the bimetallic molybdenum tungsten alloy matrix without distorting the lattice.